For this video, I'd like to explain the question, same tree, which is problem 100 on Leetcode. We're given the roots of two binary trees, P and Q, and we're tasked with the the responsibility of writing a function where we essentially want to check if both of them are the same or not. And them being what is defined as like structurally identical is that not only are they placed in the same place as it were, but they also have the same value. So you can see in this case, 1, 2, and 3 here are in the same position. So you sort of have graphically, you have the same shape as it were, and you also have the values there. So it's sort of a two level thing. For this one here, as you can see, we have, let's see. Both of these trees are actually not the same because, this tree here, we can see it's placed off to the, to the left. And here, the child of 1 is placed off to the right. And so it really, we really want to make sure that, children are placed on the same side and they're of the same value and they have the same parent and so on and so forth. This is the recursive code for that function. And we actually, the motivation is to actually draw this out as if it were, an iterative approach. And then judge this. So as you can see, we have two trees, tree 1 and tree 2, and the P and Q pointers are actually at the roots of both of the trees, the ultimate roots, the absolute ancestors, as it were. And you actually have the method here that accepts both of these tree nodes, P and Q. And so really, the first case here is to say, okay, well, if they're both null, then actually that would constitute as them being the same. Because if you have a P pointer and a Q pointer and they both point to null, then you actually want to say that those are the same tree, because two empty trees are the same. In other cases that either one of them is null and the other isn't, right? And that gives birth to two possibilities. Either you have P null and Q not null, or P is not null and Q is, or P is null and Q is not. In both cases, since we have sort of, in both cases, since they're not matching, we return false. We'll see how this works into our recursive definition. Here, if their values aren't the same, and actually you can combine this up here in some fashion, but if their values are not the same, then if P and Q are pointing to two different things, then the idea is to sort of move P and Q in tandem. And if they both point to different things, then they won't necessarily be the same tree. But we've passed this execution, and then we come to Boolean left tree match. And these are two Boolean values that will return true for a given node. So for each node, these Boolean values will resolve to whether or not the left tree matches the right tree. So, for 6, we will have a left tree match, I'll call it an LTM, that will either be true or false. And then we'll also have a right tree match, RTM. So this will, eventually what's going to happen is we're going to bubble up a value of true or false or whatever. And suppose both of these came out to be true. And again, it's really not on the same tree. What's happening is, it's asking, okay, well, is when we work this way for the left tree, do they match? So if this comes out to be true and the right tree match also comes out to be true, then we know that for 6, both of these trees are the same for the left tree of 6. The same thing will happen with 4. You know, we'll bubble up a value here, we'll bubble up a value here, and then for 6, left tree and right tree match will both come to definitive values. Will return if they're both true or both, you know, what the verdict is there. But so for each node where, you know, we are looking at the left at one given time, and then it gets returned back up, and then we also look at the right recursively, and you know, a verdict is then passed that, okay, on tree 2, your left is the same, and on tree 1 your left is the same. And so if, you know, and then you do the same thing for the, you know, for the right, although I was pointing to the right here, but you do the same thing for the right on both trees, and then, you know, you bubble up a verdict. And so we'll see how that, you know, works line by line. But where we were left off with is, okay, you know, P and Q were passed in, and remember P and Q, so this was 2 and this was 2. And what we did was we said they both weren't null, either or weren't null, and both of them had the same value. So this if block was not satisfied here. And we started working our way down the left tree. So recursively, what happened is, okay, then we called is same tree again. So we actually produce a copy of is same tree. And this time the parameters that it accepts are P equals 6 and Q equals 6. So P equals 6 and Q equals 6. And, you know, they're both not null, either or are not null. And they both have the same value. So this if block is not satisfied. And so again, left tree match is called recursively. So left tree match is called recursively again. And this time it's called on P dot left, Q dot left. So P, you know, we were at 2 before. P then moves down to 6. Q gets moved down to 6. And, you know, now we then produce another, you know, so, you know, 2 does not have a verdict yet for what the left tree is, because it has to judge the subtrees of the others, right? So, and the same can go for 6. 6 does not have a verdict for what its left tree matches, because it has to judge the subtree for the others in order to do that. In order to say that, see, the thing is, for this problem, what you have to recognize is, in order to say that 6 has a, you know, 6 has a the same left subtree as 2, it needs to be able to judge the subtree of the others, and that's why this problem is perfect for, you know, recursion. And so, you know, we go ahead and we say, okay, well, P dot left, Q dot left, we call it again, so we produce another copy of is same tree, and this time it is accepted for 8 and for P equals 8 and Q equals 8. And again, they're both not null, either or are not null. And you know, they both have the same value, so we don't execute this either. But again, I mean, so now we call, since all of those 3 conditions were not satisfied, we call is same tree again, and is same tree is called again, and this time, you know, the parameters for the left and the right are actually null, right? Because when you're down here, when P is down here, you know, these are both null values. So what happens then? P is null and Q is null, we return true. So what happens is true actually gets sent upward. True gets sent upward. What was waiting on that verdict? It was this line of code for node 8. It left tree match is so this Boolean, it was for 8, it's judging whether the left tree matches. And what we know is that for both of them, they were null, weren't they? So the verdict there is true. So for this, it's true, right? We know now that for 8, the left tree matches, it's true. In both trees, the left trees for 8, because even if they're null, they're still the same, right? So the left tree matches for 8, and then it jumps immediately. So now it resumes its execution now that it has a valid answer for the Boolean variable left tree match. It now then moves on to finding whether the right tree matches across both trees. So what it does is it says, okay, well, now let me start jumping to the right. And it will perform that same operation that we spoke of. So it will go to the right, it will go to the right, and then it will bubble up. What's going to happen is it'll produce another, frame like this, and both of them will return, both of them will be null. So when you produce another frame like we've been doing here, P will be null, Q will be null, you'll return true. So this actually also gets set to true, right? And again, I haven't produced that frame, but you can imagine, okay, well, now you're doing the same thing for 8, the 8th node. You go to the left, you call it on the left, and you call it on the right for that for tree 1, and you call it on the left for right for tree 2. So P dot right, Q dot right, and then they're both going to be null. So whatever how that frame looks like, P is null and Q is null, so you actually return true, and they're both the same. So this is also set to true, right? And so the verdict for 8 is that the left tree matches, right? The left tree matches and the right tree matches. So true and true will result to true, right? So this verdict for 8, like 8 being able to judge that its right tree and left tree are the same, was helping 6 judge whether its right tree is whether its left tree is the same on both. So it really goes both ways here. So true is sent as the final verdict. It's sent upward. True is being sent to, and all that does is it helps 6 come to a value of whether or not its left tree matches. So this is set to true for 6. But then now that so it has been able to judge, whether or not, it has the same left subtree across both trees. Now it wants to jump to the right and say, okay, well, what about my right? What about my right? And what it will do, we're on 6 here. So what it will do is it will say, okay, well, it's going to come down here. It's going to come down here, and it's going to ask, okay, now P will be here, Q will be here, and it will produce yet another frame. So let me pull up another frame here. It will produce yet another frame, and it will accept 4 as that value. It's going to say, okay, well, this is 4, this is 4. Are they both null? They're not. Are either or null? They're not. Are their values different? They're not. So then 4 will now ask the same set of questions to validate whether, because now, again, so with 6, we want to, ultimately our question here is to answer what 6 is, whether its right subtrees are the same across both trees, right? But the problem is that we can't know that until we know whether 4's left and right subtrees are the same. So now that we have entered in 4, it is now asking the same set of questions for 4. It's going to say, okay, what's my left subtree? And then it's going to obviously produce, it'll go left, and so it'll go, to the, it'll go to the left, and it'll go to the left here as well. Both of those will return null. So the verdict here for the left is true. So this one gets set to true, and then it'll do the same thing for the right. It'll move to the right across both trees, and this verdict will be set to true. So left tree matches and right tree matches. So this will be true, and true will be true. So the verdict across both trees for 6 will be true, and we can return here for the right. On tree 1 it was true, and then on tree 2 it was also true, and so left and tree are matched. So this is now true. And again, I mean, so this verdict is then sent up to 2, and 2 then asks, okay, because 2 could only know, the thing is that, 2 could only know whether its left subtree was the same across both trees, if and only if it knew whether, 6 had the same on the right and the same on the left. And then 6 could only know whether its left and subtrees were the same for both if it knew, if it knows that, what I have, if 8 knows, whether I ask what's on my right here and what's on my right here, are they the same? If I ask what's on my left here, it's on my left here, are they the same? And then, it then brings up the verdict. So 2 could only know if 6 knows, and 6 could only know if 8 knows, and 4 knows, and so on and so forth. And so therefore, now the verdict for the left is true for 2. So now that it has a true verdict, it then asks what's on my right. And then now that we've reached sort of the, the highest order here, now we start actually asking the same set of questions on the right. And so, is this the same tree? It says, okay, well now, P will go to the right here. Q will also go to the right here. And, they will basically make another stack, they will make another recursive call of their own, where now 3 is being accepted, and 3 is being accepted for both of them. And since they're not null, and since they're not, since they're not, since either or are not null, and since their values are the same, they now 3 has to start asking the same question as 2 was before, which is, okay, if I go to my left on both of these trees, do I get the same value? If I go to the right on both of these trees, do I get the same value? And then when it asks it for 8, it will ask the same question again. And then when it asks it for 1, it will ask the same question again. And so this process will be repeated. So what's going to happen is it'll ask the same question for 8, and 8 will basically say that, when I ask my left across both trees, I get the value of true. And this will bubble up true. So, for 8, this line of code would be true. And then it will ask for the right. Both of those are null across both trees. And so it will also be set to true. And so the verdict for 8 is true. And then 3 will finally know that whatever it has on this end is true. It's the same across both trees. And then 3 will then begin to ask, it on the right, because now this line of code will begin executing right tree match. And, then what would happen in that case is 1 will then ask the same question that 3 was asking before, which is, if I go to my left or my right in both of these trees, do I get the same value? And it will say, okay, well, yeah, if you go to the left, you get the same value, it's true. And if you, on tree 1, if you also go to the left, come from the left on tree 2, it's also true, they're both the same. And then it will do the same thing for the, for the right, both of those will be true, and true is true. So one will basically say what I have on my left and right is true. So 3, you should be good from that side. And then 8 will say the same thing, from that side, you should be good. And so 3 will say true, and then it will bubble it back up to 2. 2 will have an ultimate value of true from that side. And then of course, it has an ultimate value of true from that side as well. And therefore, both trees are the same.